All
Screen.
right. Hey guys, what's going on? Me, I apologize. Totally late, totally my fault. I had a stolen motorcycle. But that's a story for a different time. But we're going to be being joined by Echelon here again, and we're going to be going over some of the immediate uses as well as some of the future superpowers of the virtual physics library. So, Echelon, you had something you wanted to share?
Okay, let me share my screen. Um,
All right.
Let me share one screen so it's easiest with two monitors. Entire screen, share this one.
Oh, okay. Got it. All right. There we go.
I did an interesting query. I asked Bard to read the library and assess it for me and tell
Mhm.
me what's there. And so I asked him, I said, can you read as much about the Eschelon Azha virtual physics library and summarize what it is and what it does and what impression you get from reading as much as you can about the code? And he actually did a pretty good assessment, and it's a good starting point for actually the discussion. He
Hmm.
did a deep dive, blah, 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 reading. This is what I gathered, what it is an experimental library that seeks to create a physics inspired framework for software development. That's absolutely true. And it isn't, I would definitely say it's experimental.
Hmm.
Aims to achieve simplicity, stability, and intuitive understanding by drawing parallels between software and elements and real world physics concepts. That's what the whole point of the library is.
Hmm.
Offers building blocks like atoms, molecules, and compounds representing data fields and their interactions. That's true. Introduces novel concepts like force fields and energy exchanges to govern data flow and behavior. What it does, it provides tools for building software systems with physics-like properties, potentially leading to predictable and robust software due to its inherent structure and physical laws, simplified design through modular components and clear interactions, intuitive understanding of complex systems by leveraging familiar physics concepts, focuses on data transmission with a unique approach inspired by physics, possibly aiming for efficient and precise data exchanges. And I'll cover more details on that as we go forward. His impression, an ambitious, intriguing concept with the potential to reshape traditional software development approaches. I think it's pretty radically different than what we're doing now. The implementation seems to be in its early stages with limited documentation and code examples. Absolutely true. This is very early stages and there's limited documentation. While the physics analogy is interesting, its practical applications and benefits in the real world projects remain unclear. And that is true. I've had a lot of experience working with different iterations of this. I found it to be pretty practical and it works. I think the latest version is even better, but that's will take time for people to assess using it. Further exploration and user feedback are needed to assess viability and effectiveness in software development. True limitations of my analysis, I cannot fully grasp the intricacies of the code. The lack of comprehensive documentation limits my understanding. Overall, the Echelon Azha Virtual Physics Library presents a novel idea with exciting possibilities, but further development and community engagement are crucial to validate its potential in the software engineering world. So I think this was a pretty good assessment of where we are. I was borderline on not even releasing it at this point because it's very early, but there are uses um, for this library that are actually valuable right now. And I wanted
We
to
were just
go
talking
over.
about a few of them the other day. Yeah, you were just saying about it could eliminate potential current libraries that seem to be taking a lot of computational effort.
Yeah, especially in data communications. It could be used as is, mainly for Kotlin programmers. I've made several changes that are kind of non-standard Kotlin with the aim of being able to generate Python code, Java, and possibly TypeScript. I'm borderline on whether that's worth doing. We'll see as time goes by. But right now it's Kotlin. You need Kotlin on both sides. So if you're doing client server development, you you'd have to be running Kotlin in both places. And I'll come back to that, but a good tool for using it is Google in Android development has a tool called Jetpack Compose for building Android applications, and JetBrains has kind of picked it up, and they're making it their multi-platform development UI tool. Maybe I'll just jump over there real quick.
Because I was going to say that's a newer tool within the past few years. I think they released it right as we were shutting down the world, so it was a cool new idea at the worst possible time.
Right. It hasn't really taken off, and it has some stiff competition. It's competing in the browser side with mainly JavaScript and TypeScript, and Angular and React are pretty big juggernauts in the industry, but they're not completely cross-platform. This, because Google developed it for Android using Kotlin, since Kotlin is pretty much the standard language for Android development now. They did a good job of integrating a UI tool. I've dabbled with React for Kotlin. It's not really the same as React and TypeScript, and it feels a little hokey to me, where from what I've seen so far of Jetpack Compose, it's closer to being a Kotlin feel type library. So there's some interesting things. They're in their early stages of where they're going with it, but their goal, since Kotlin pretty much runs everywhere, having a UI tool that runs on iOS, Android, desktop, and web is pretty cool, pretty compelling. I can see why they're interested in doing this, but this talk isn't really about JetBrains and Jetpack Compose. It's more about virtual physics and how it fits into there and what you can start using. And I'm not going to go into the library itself and how it works under the covers. That'll probably be for another talk. I'm going to go with what is in the test application. If you go into the test package, I have a run me, and I'm doing some tests, and I'm going over what you can use now, which would probably be most interesting. And the first of it is the elements. So let me talk about that. With the elements, you're really creating records and structures and objects that are self-emitting. And you have the option of carrying your metadata. So for example, here's an address record. It's actually not a record, it's a field. I have address, city, state, zip. So if I go to the atom, here's an atom. It extends lithium. This is, whoops, I didn't mean to paste in there. When you create atoms have multiple protons. The minimum atom that you can create is hydrogen. It has one proton and one electron at the bare minimum. You can't have an atom without a proton. So by default, if you look at the hierarchy, lithium, which is a type of atom with 3 protons, it extends atom and it adds 2 more protons. So normally you would think, oh, lithium has 3 protons. Why are there only 2? Well, that's because the mere fact of extending atom, you get your first proton. You cannot have an atom without a proton. So lithium adds 2 more over hydrogen, the most elemental atom you can have. And what it's saying, the values themselves, if all you wanted to do is carry values, an address, a city, a state, just a value, then a hydrogen atom is enough. The first proton carries the value. But if you want metadata like field name, axis level, other properties, colors, things that you want to carry with this, well, then you need a bigger atom. You need multiple protons because it's carrying multiple values. So in this case, lithium, you use lithium if you're passing a value that passes two additional pieces of metadata. So if we look at the address field, it extends the lithium. The value is stored in the first proton, but now I'm creating a field name proton and an access level proton. The field name of address is address. The field name of state is state. If you had a form and you wanted to pass the field name and build a generic form builder that just takes a molecule made of atoms, and you wanted to build this form at minimum, you could iterate down the atoms on the molecule and say, okay, I have one atom, it's called address, take the name, put it on the form, and then get the field. And you can look at the access level. Okay, this is read-only, so I'm going to generate a read-only field. If all these fields are read-only, you could basically have a generic form builder and pass all the metadata in the molecule, and you can just build a generic form with any kind of record.
So
Right
it kind
now,
of makes it easy to create. Sorry to cut you off.
mm-hmm.
It makes it easier to add classes as well as have data protected, so that if a bunch of folks are working on something, one person isn't going to do something and throw everyone for a loop.
Well, right now, this is informational, the access level read-only.
Okay.
It's a suggestion to the form builder that you should make this field on the screen read-only. They could make it open and they could pass it through, but one of the next, it's not ready now, but one of the next superpowers actually is that in the quarks are going to contain format and constraints, so that if you build it into you can certain constraints will be predefined, like very common things, like for example, something should be string, date formats. If this is a date, there's going to be certain constraints. You can add your own constraints after that. That's not available yet, but once that's available, the constraints will not allow you to make a modification. It'll be built into the atom. You will not be able to set it. When you try to set it, you'll get an error message back saying, I can't set this value because it's read only, or I can't set this value because it has a numeric constraint and you're trying to set it.
It's going to tell you what the problem is when you're debugging and everything. So, um, can we get back to, sorry to cut you up, but focusing on like the immediate benefits, like what somebody could use right now? Because we were talking about it a little the other day, and it sounds pretty good.
Yeah, what we can use right now definitely is focus on the elements. You want to create elements into compounds. And once you have a compound, it's very easy to transmit. And I'll give an example. I haven't released the server. I suggest if you're using any server that works with Kotlin, stick with that. And any UI tool, I would recommend this would probably work best with, I suppose, if you want to use React for Kotlin, this should work pretty well with that. Or Jetpack Compose, something that's geared for Kotlin running inside the browser. By using this, you won't have to use any JSON messaging, or you won't have to do parsing. You can just reconstruct the objects. I'll demonstrate that with my own server. I'm working on a custom server. I'll talk a little bit after this about where I'm going with this, so that, as people looking at the kind of big picture, what the direction of virtual physics is. Borderline on whether I also want to build a web development library, but I'm not so sure I want to go down that path because there's already React, Angular, there's just an awful lot out there. I'm more focused on 2D graphics, a separate library where there really is nothing in that area that kind of exists, and it would work really well with virtual physics. But what matters most is how can you use this today? How can you get started? And, begin with the simple things and then learn more about it as it goes along. And so the first thing is creating atoms and compounds. If we look at, let me go to the RunMe. If we look at radiation test, and one of the reasons I'm not using standard testing tools is because ultimately I want to generate this for many different languages. and a testing tool that works with TypeScript won't work with Java. We may be using JUnit on Java, and there's a whole bunch of testing tools for TypeScript. So I'm kind of just writing my own simple test cases, and these things should be able to run in multiple languages without needing any. And another thing is I'm trying to avoid having dependencies in this library. If you notice, you don't even need Maven. There's no dependencies. It depends on Kotlin, and that's it. And the environment, if you're using Kotlin JS, whatever the Kotlin JS dependencies are, if you're using Kotlin running on the JVM, then whatever those dependencies that Kotlin has, but I'm not adding any dependencies. And
That sounds like it might streamline a lot of things.
It does. It makes this thing very tiny and easy to use and nothing to break. I'm not dependent on, this version of some messaging library that when it upgrades to 2.0, then maybe some of this breaks, and nothing can break. It's kind of rare. They're not likely to change the Kotlin language in a way that the code breaks. So I think they will deprecate any functions that are in the Kotlin standard library with many years notice if they're making any breaking changes. But I think there's probably nothing in here that can break with anything changing, because this is kind of at the bottom and doesn't depend on anything other than Kotlin. And when I generate the Java and the Python version, that rule will still hold too, because I'll still have my custom testing tools, and everything will be written from ground up. So that's not a concern. Definitely not, because I'm pretty adamant about not introducing dependencies. It'll be a cold day in hell before I do. So the idea of this is you create your atoms and create your molecules. Let me go back to the atom to give some examples of it, where the metadata is useful. You may not need it if you're just transmitting values, but here I created an address atom. I'm using, instead of putting, this may look a little strange, I'm constructing this with a field rather than passing it in the constructor. The reason I'm doing that, different languages like Java, Kotlin, Python, TypeScript, all have their own unique ways of doing constructors. So to write a transpiler that can transpile code with multiple constructors in one language, how do you generate that in another language that doesn't support multiple constructors? What I ended up doing is coming up with my own convention that will translate easy between all the languages, so that when I write a transpiler, I'm more translating syntax and not translating semantics, because that's a much more difficult problem to solve. So I had to make some compromises, but in the end, I kind of like it, because it also means if you're reading Python code or you're reading Kotlin code, it'll look very, very similar. Other than certain clues in the language where, if you see the keyword fun, for function, it doesn't exist in Python, you're in Kotlin. But if you're looking at the actual code, we don't have val, but everything else would look nearly identical. So
it's fairly obvious, because even I am like fun. I'm like, I like fun. I'm like, it probably means function.
Right. And in JavaScript, it's spelled out function, but the rest of the code will be nearly identical. So
even a noob like me can start to parse what's going on there. I'm like, all right, so it's all strings, all right, maybe an integer, all right, this, that, the other thing. And I assume as you would go through, it's going to let you know if you're making a mistake or something's not lining up, like basically like any debugger or something.
Exactly. And here, like if we look at address, I'm constructing an address. Let me actually go into it kind of step by step. I construct an address atom. I'm going to extend lithium because I want the value plus 2 more fields. And it's probably pretty typical. You can make it dynamic, but most times if you're passing metadata with something, it's probably baked in. The field name of address probably will be address. You should build it into the init function. And the access level, you may want to change it. You have access to these protons. So, for if the user is Bob, maybe they can only read the form, it'll be read only. But if the user is Mike, maybe, they have the access levels to edit it. You can determine that on the server side, find out who they are, what their rights are. And if somebody is read only or no access, you can basically just stamp the entire record with the access level and ship it over the wire. And on the client side, you can now have very elaborate field level security, which is something that's very difficult to do normally, because when you start having interactions of groups, I'm a member, I'm an individual, I have read-only access. I'm a member of, the zip code editors, but not a member of the street editors, for example. It's kind of a nonsensical example, but, I could be in multiple groups. So on the client side, figuring out field level security is really pretty much impossible. You need to figure it out on the server side and stamp it. And then when you go through, you look at it and say, okay, I'm a member of a group that can edit zip codes and states, but not addresses or phone numbers, for example. I can change.
It allows you to specify.
Right. So, it goes through, it evaluates it, then passes over the record. And let's say I had zip code and social security number and I'm only allowed to change address. It would make those fields editable, and all the rest would be not editable or no access at all. And it goes to the user interface, and the user interface can now read this metadata in the atom itself. It knows its field name. Maybe you want some special colors that you want it to look, but this person doesn't have rights to change anything but address. So now you can do true field level security with this, just building it into the atoms and doing it on the server side, validating what group people are in and stamping the records. But for example, I kind of hard coded it. It's read only. I have no client side right now that's actually using it. It's an example of how it works. So I built an address in the city and state. I did it for all the fields. They pass their name and they're all read only. And so if we go back to elements, I created this address atom and I'm going to omit it. So this has, actually, let me run it with the debugger because it's easier to see. I'm going to run it again and stop right at that breakpoint. Okay, right here, my original copy of this atom, I'm going to omit it. So I have this emission string. And you can kind of think of it as DNA of the object. Everything is in there: the field name, the access level, any other metadata that's in there, the entire structure, the structure, protons, neutrons, everything is in this emission string. And so I emitted it. Now the idea is this thing you're going to send to the browser. You're going to send it to a React program written in Kotlin or Jetpack Compose. They're multi-platform. Let's say that's what you're building a UI with. You send this emission string over, and the first thing you do is you materialize it again. So you now have a clone, and I'm going to cast this clone back to an address record. And when I do that, if you look at this address, see its address here, it's a complete reconstruction with a very deep copy. If you were using JSON, you would have an awful lot of string and metadata and type within type, and you don't have class information in JSON. So if you're trying to go across different languages, you would have to parse it using something like JSON, or maybe using protocol buffers. And you would have to construct a new object on the other side. And maybe you'll ignore some fields. Maybe you don't care about all of it, but you'll end up reconstructing what you need in some way that you need it. This just makes an identical code, an identical clone. And you also have your field name. If I want to get this out of it, I have the clone. I'm on the other machine, my access level and value. So if you look at it, It made the clone. The field name is address. The access level is 0, which is read-only. -1 is no access, and +1 is editable. And the value itself is called elements with an exclamation mark. That's how I constructed it. So you actually have an instant clone of whatever you sent. If you have multiple fields or records, I'll show that in the other test case. You can actually create records. A record you can think of as a compound or a molecule of atoms. When you build that, you can transmit the entire record and the whole thing will clone. And so it becomes very useful. And, with my test case, I'm just testing to make sure it's true, and it worked, and it did. So this eliminates the need of using JSON in special parsers or using protocol buffers or, God forbid, transmitting with XML, which becomes very verbose. You basically eliminate the transmission. So that alone makes this a good tool to start with and begin working with. And let me go back to the RunMing and go to radiation, because this kind of reiterates what I'm doing, what I just kind of demonstrated. This is creating an entire row, and let's talk about that. In this case, a record you can think of as a compound. A compound is basically multiple atoms combined together in chemistry, and you have a compound. So this compound has name, address, city, state. I could have added zip as well, but for example. And what I'm doing is, you'll see I'm adding these things to the molecule. I'm not assigning a local variable, because you want this to be able to clone itself and to emit itself. If I did something like this in my storage, if I had val name, and I put equals name here, I could do that, and I can create my own custom structures, but I would have to write a custom radiate function. I would have to radiate this in the right order and also absorb it in the right order. And for now, it's probably not necessary, because you can just use what's built in and it'll do it automatically. But I will make some classes on how to do that if you want to build custom structures. I don't know too many things in the universe that are not built on top of atoms, so I don't know why you would ever need to do it. But if some miraculous case comes up and you need to create a class that has some unusual properties, you can do it. But I kind of don't recommend it, because you're stepping outside the boundaries of physics. And in theory,
Well, I mean, I think it's just interesting. It's like the way you're explaining it, just even from just like a semantic uh, viewpoint there, it's like, all right, compound. Compound may be made of different elements. Well, what do you have here? Oh, it looks like the way you're describing its actual use, that sounds like a form that I've seen a lot of times on the internet. Okay, oh, look, what's one element? All right, name. Oh, look, address. This, that. I'm starting to get a feel for how these different things would work together for a lot of things that we deal with on a regular basis.
Yeah, and as a matter of fact, this adds a new there is a new hidden superpower in here that I really haven't talked about, because I may have mentioned it a little bit in the README, but when we think about interfaces, we can define the signature of an object. Say, it must adhere to this interface, it must have these functions and have this signature. Maybe it takes a string, or maybe it takes an atom. But we actually have a new kind of scoping now, because name, address, city, state, if I had zip extend lithium atoms, I now have an atom in my form builder. My form builder can now have a new kind of interface, and it says all my atoms must be, for example, lithium. I can't
So
take
every
hydrogen.
time you use lithium, you can now go back to what you already have rather than having to construct a whole new thing.
Right. And the form builder, if you pass an atom that's hydrogen, the form builder knows it can't use this because it's missing a field name. It's expecting 3 protons. It's expecting, if it's checking the access level, then it's expecting a proton that has the access level. You can't really do that. This is a level of abstraction higher than the level that we're currently programming in. You can't really say, I'm expecting a list of 3 fields without actually writing the code and checking, did I get 3 fields? Did I get a value, a field name, and an access level? I'm expecting this list to be 3 elements long.
So Echelon, it's, and again, I'm not a programmer by trade or anything like that, but it sounds like one of the benefits a lot of folks like with programming kind of as is, well, you can do anything. The double-edged sword, the other side of that is, since you can do anything, you could say, oh, let's do this. And now maybe it won't work, but you could probably like hack it, so to speak, to get it to work. But in this, it's like if it's expecting something with 3 protons, it's expecting lithium. If it doesn't get lithium, that's like, no, that's not how this works.
Exactly. And if your form builder is expecting a molecule of all lithium atoms, the minute it tries to cast this thing to a lithium, if it's hydrogen, it's going to throw an exception. You don't have to validate. You don't have to check the size. It's not lithium. And so now you're thinking at a higher level of abstraction. If you kind of think of it, when you're thinking, it's rare when you'll need to go below atoms. Most of the world, we don't deal with protons and electrons except in electronics, and I'll come to that. Where for the most part, we're dealing with atoms and molecules and compounds, and we don't need to go lower. The library itself is dealing at the subatomic level to get a lot of these things done. But we really want to begin, for the most part, at the atom level. We don't really want to deal with things smaller than atoms. The library allows in the transmission, you can transmit a loose proton from machine to machine or a loose electron. It'll allow you to do it. Anything that extends from particle, which they are, is transmittable. But if you're doing that, you probably need to ask yourself, is this a best practice? Am I going about it the right way? You kind of want to be at the chemistry layer when you're actually working with this and building applications, which is the real world. When I'm building a house or building a desk or building a computer, I'm dealing with compounds. I'm not interacting with protons anymore. Like, that's below. So if you think of it, to actually use this library, you want to think on a chemistry level or an electronics level, or, building up from that. So we now have a higher level of abstraction. I can now say that I have a form builder and it takes, a list of, from 0 to infinity, like however long you want to store lithium atoms. If I wanted to also pass the color, this form builder lets the server decide the color. Like if it's negative, it'll be red. If it's positive, it'll be green or black. Then the server can stamp the color in it, and the form builder goes, in that case, what's after lithium? Boron, I think. It'll expect a list of boron. And now it knows it can build this form. It can set the color. If it's missing boron and it has lithium, it can't set the color. And, you have an error condition. The server is not sending what it wants. So we can think at a higher level of abstraction and think on a chemical level. And this is kind of a superpower. This is what has kept me going building this library. This is another example. I didn't set out to design this. It wasn't my idea that, gee, maybe I can use, an element and, come up with a new level of abstraction where I have higher level interfaces that don't exist in programming. I didn't think of that. It happened by accident. When I was doing this, it was like, wow, damn, I have a new level of abstraction that I can now think on the chemistry level and not, and it's like, wow, well, this is what kept me going. The more authentic the library came to the laws of physics, many times I wanted to quit. I kept thinking, this is impossible. I'm never going to finish it and I'm never going to figure it out. But damn, like these superpowers keep coming out. It keeps exposing new super abilities that I didn't design. I didn't think, even this right here, it's kind of like, wow, I didn't think that we can do that. It can admit itself. It could, replicate. It could clone itself. It can validate itself. It just has this incredible structure that copies a proton with the quarks. Why are there 3 quarks? I don't know. Like I didn't try to cheat. I didn't try to put 4 quarks. There's 3. And I started looking at it like the laws of physics must be telling me something. There's 3 pieces of information. You can look at physics from a mathematical point of view, but you can also look at it from an information point of view and say, what secrets are hidden in there? Why is it structured this way? And if you can find the right interpretation, which was really the hardest part, you can all of a sudden see that there's something magical happening. Why is such a tiny library so powerful? Well, you can say it's a coincidence. And, I could have named Proton Betty and, given it a new name, and it's not physics, but the pattern is still there. No matter what I name it, it has that pattern. And somehow building programs with this structure and these patterns keep manifesting superpowers that I'm not designing. And I don't know any point in my career ever that I was able to build something by accident and have superpowers that I didn't design into it and that I didn't think about up front. And this has happened so many times to me that it has a superpower that I didn't design, I didn't think of, I didn't even imagine. I've never used any tool in any language in any way where the result of my work was greater than anything I ever imagined. It's never happened.
It's something that when it pops up, it warrants, that's funny. Why is this the case? Why is it that when we're using similar logic for programming, as appears to the best of our knowledge within physics, seems to have very similar logical things going on?
Right. And I believe, it's a philosophical debate. People can be on all sides. That's fine. I believe that these patterns, that in a way, the standard model of physics behaves like a computer, and there's a message in there. The organization is not only the ultimate Lego set of the universe, that you can build everything in the universe if you interpret it correctly and say, hey, can I use that in my programming? Then it's just the ultimate Lego set of programming. And it's what I believe. People could debate, why is this so powerful? I don't know why. I'm open to all points of view on it, but here we have chemistry, and you can do so many things. And I have some sample code with catalysts, and it's very rudimentary, but there's some really powerful things that it could do that I didn't really think of up front. I just started. I've worked on this for 22 years, and I failed every time I tried to do it because I tried to be a good programmer. I tried to use my imagination. I tried to be creative. And I found that at every point where things went wrong, it was where I invented something. And the things that worked really good were the things that were really authentic to the laws of physics. And what I changed in this last iteration, I just said, you know what? I'm not going to be a good programmer. I'm not going to invent anything. I'm just going to copy everything. And I struggled a long time. Like, what do you use a neutron for? Like, why is this pattern here? What do you use? Why is there 3 quarks? But the more I kept at it and decided not to invent anything, if you look at this library, it's just filled with just particles. It's one after another. The entire let's go into, I moved this into the dictionary. If you look at the absorber,
A little bigger. There we go.
is my screen. These things are, I'm going to rename this, but we have like for the atoms, Boolean different type. They're kind of helpers. Actually, that's like a good segue into something else. But
Keep going, Echelon. I have to run outside to see my neighbor real quick, but I'm still
okay,
listening. All right, continue.
okay. So basically, if you look at when this runs, actually the best place to see it is when you run it. Let me just run it. If you look at all the particles that are coming out of this, these are extensions above that. You can kind of think it, on the development level higher up, but I have molecules and, it's just, I'm using subatomic particles all the way down. Once you get to the atom down, I'm not inventing particles. They're all there. So that's what I think makes this thing so powerful, makes it worth learning. And it's kind of philosophical as you step through the code and look at what's happening. A lot of times I'd look at it and say, man, this means something, but I don't know what. So with that being said, I created an address row, and here's this address row. It's just like an atom, except this is a compound. I'm emitting it. I have an emission string, and I'm materializing. It's a clone. Basically, you would send this to the other machine, and you can have your metadata and all the other things mixed in with it. So this is very powerful and very useful. Let me go to the next thing you might be interested in using. Neutrons you may or may not want to use. It's such a, again, this was something that kind of shook itself out. I kept thinking, with a neutron, what use is a neutron? It has no charge. It just makes it heavier. It doesn't interfere with chemical reactions. It's just bulk weight. Until I realized, oh, you can store prior values and do rollbacks inside of neutrons. So I can, here I have an address row, and I change the content from name to name to, address to, and so on. And I do the beta decay and roll it back. The neutrons convert back to protons and discard it. So you actually have kind of like commit and rollback built into your records. So that would be useful if you're building a form and they had a reset button and they started change. They had access to all the fields because you had access level, it's editable, read write, and they changed the form and they didn't like it and they hit reset. Normally you'd have to have a backup copy of the record and copy it back into the form and all that. With this, you can just do beta minus decay. If you know that you have that option, you do beta plus decay. It basically takes all the values in the protons and adds it to the neutrons, makes a new isotope. It doesn't change the chemical. It doesn't change the atom. Lithium is still lithium. None of those properties change. It doesn't interfere with its chemical reaction. It won't interfere with the kind of the type that you're using. It just creates a new isotope. And if everything is good, you don't have to roll back. But if they hit the reset and they want to go back, you just do beta minus decay, and all the neutrons, it decays back into protons, and you have the original value back. So you
It's
may or
funny
may
how
not.
that works. No,
Isn't it?
because that's an yeah, beta plus and beta minus decay. Yeah, those are things.
Yeah, and it exists in the real world, and we needed a way to, have commit and rollback without interfering with the atoms. And lo and behold, isotopes are built in. And, if you interpret that's their use, and since we do know that protons and electrons can become neutrons or vice versa, there you got it built into the atom. So that's something useful you may or may not want to do.
Oh, Nuno's getting fascinated. He's like, they're like very interesting. That analogy with the standard model kind of programming language. I think, and Nuno's from, I met him, from the greater Wolfram community. So it's, There's more and more attention being paid to this, and Stephen Wolfram is one of the champions, I would claim.
I think this is worth. It's odd to say that after all these years of working on it, like I'm not at the end, I'm at the beginning. I finally released this library with just enough to say that virtual physics begins. Because, and I'll talk about some of the things that I, want to do and where it could possibly go. This is just in the infancy. I actually think, it's philosophical. I think it flies in the face of the way we're currently doing programming. And one of the things where it puts a severe blow is the functional programming crowd. And the reason I say that, the claim to fame of functional programming, which makes a lot of sense, is that you don't want to have side effects. Objects are evil because, if you have some state and I say add some value, you're going to get a different result if the state of the object has some instance variable that's set. It's
Yep.
non-deterministic. So the functional crowd says that's evil. Object-oriented programming is kind of a bad thing because you have state all over the place. It's unpredictable and so on. But what I've learned from working on this is actually the universe has state everywhere. Absolutely. If I have a pen and I leave it in the dashboard of my car in the winter, the ink is frozen and it won't write. But if I have the pen at my desk, it will write. Now, that's a functional programmer's nightmare. It's like, whoa, there's some side effect state that you can't see, which is its temperature. But I feel like we got to deal with it because every particle, all the way down to the subatomic particle, carries state. It carries temperature, charge, momentum, like you name it. So engineers have no such luck. Like the functional programmers want to say, okay, we'll just have a stateless universe. But the fact is we don't have a stateless universe. Real engineers know how to deal with it. When they're building bridges, they make an assumption that this bridge won't heat up to 1,000 degrees. If somebody says we're building this bridge maybe on Venus, I don't know how hot it is, maybe we won't use steel or, and so on. The engineers have to deal with state. And so I believe, and it's philosophical, people can disagree, that the laws of physics make a true programming model and we have to copy the way it really is. And if we want to do true software engineering, like they call us software engineers, but we're not engineering anything. We're real engineers are governed by the laws of physics. We're not. Until this, we need to be governed by the laws of physics. And according to the laws of physics, state exists everywhere, so deal with it. So that's why I say this flies in the face of functional programming. It really puts a question, is there such a thing as a stateless universe? I think not. If this universe were stateless, I don't think we'd be here. Like, I don't know what would be here, but it wouldn't be us. So
just to steel man what you just said, Professor Roy Kerr, one of the founders of the Kerr-Schwarzschild solution for black holes, for rotating black holes, he recently published a paper, and in one of them he has a footnote where he's like, well, my astronomy friends, I'm paraphrasing here, are like, well, their simple question for the beginning conditions is, what is the equation of state? So apparently that seems to be a fundamental thing.
And it's a really good question because all of our calculations, if it ignores state, it's incorrect. It doesn't account for the true nature of anything. So I think what this does, it encapsulates state exactly the way we do in physics and tells us that we actually have to deal with state. So, these things are really useful. Depending on what you're writing, you may want to use the neutrons. You may want to have rollback. Not all applications have a need for it, but if you do, bam, it's really easy to do. You don't have to give it a lot of thought. The radiation is amazingly useful because you don't have to use JSON and protocol buffers. And, at minimum, just send a message with that string. That's the easiest thing to do. The string looks very strange, but it's base 52. There's nothing but lowercase letters, uppercase letters, 26 times 20, 26 lowercase, 26 uppercase. It's base 52. I could have used numbers as well. It would have been a little bit more condensed. You could put more data in 2 bytes. But the problem is when you mix numbers and letters, it's very hard to debug. Is this an O, uppercase O, a lowercase O, or a 0 when you're trying to debug the data? Is this
So you were even thinking of us humans too. Thank you, Echelon. Because no, as you're describing that, I mean, anybody that's ever done something like that, like, is that an uppercase I? Is that a 1? Is it an L or something like there? And then base 52 is, like, my first concern is, well, it's not 64. Oh, you're sacrificing all this stuff. And when I started to think about it, I'm like, well, wait a second. If within those 52, they're just lowercase and uppercase letters, I'm like, well, 52 is less than 64. If you can get all your parameters and everything you need within your library within that, I mean, that sounds like it's going to require less computation and be smaller. And I literally have like 10 minutes left, Echelon. How about this? How about we go into, you were talking about how utilizing things like radiation, how you don't necessarily have to use, like, maybe I might be confused with the JSON library and Maven and stuff like that. Some of those libraries can get pretty big and kind of clunky depending on what you're using, right?
Yeah, let me give kind of an example. Like JSON examples. Here's a tutorial. It looks pretty simple on the surface, not too different than virtual physics. I'm creating a JSON object, 2 JSON. I'm taking my user class that I made. You would have had to make a user class in virtual physics and give it a value, and you have a JSON string. And then you're going to create a new user class from this. But what it's not telling you, well, at minimum, now you have all these dependencies, right? Here's your Maven dependencies to get the right version of JSON and declare your dependencies. And right off the bat, you may forget and like, why doesn't this work? And it's like, oh, not a big deal, but you go and it's like, oh, let me put the version number and you got that in. But as you start getting into the JSON builder, you find that it's really creating, strings and objects, and if it's a complex structure, you have this object, you have to know that the user contains maybe an address record, and it's bringing it back because JSON doesn't carry class information. So it's going to become a generic object, and it's up to me to go in there and actually say, oh, this generic object with name, address, city, state, zip is really an address record. So now I have to create an address class and use that so that pass it to use the name. Oh, you also have to use the name correctly. I forgot about that. You have to name things correctly, or you have this extra syntax. Maybe there's an example of it. It's been a while.
So Echelon, just for brevity's sake, that sounds like a lot of work right there to do that. I mean, for a noob like me, I'm like, we started with JSON, and then it's like how to set up your JSON, more stuff, more stuff, more stuff. That might take a lot of resources and time.
Right. The fact that I can't even remember all the steps because I forgot you have some annotations in there, and you can annotate it that if it has this name, I wanted to use this object. Like this is getting long for a reason. So, supplying versioning and, all of a sudden what looks like it's as simple as virtual physics begins and ends right here. Like you don't have anything to do. You have nothing to install. No,
set up your classes and go.
You can go more and more advanced. And I'm sure they had a big team at Google. And the same thing, the latest thing is protocol buffers. And there's a lot that it makes protocol buffers is kind of complex because you have to create kind of your own third language. It's kind of its own language defining what's optional, what's not. You have ID numbers that if you want to reuse name and make it an integer, it better be ID number 4 because you want to have backward compatibility. So all of a sudden, you have some new tools that you have to use in addition to including this library in your dependency. You have new tools that you have to run. And again, now you have, you know, a lot to learn. There's, you know, you're learning a whole thing. And your goal is just to send a message. It's so much easier to just take the object, emit it, and on the other side absorb it, and you have a clone of what you sent, and you don't have to learn anything more, and you have no dependencies. So
That
that
sounds a lot
alone,
easier.
yeah, I think that alone makes it worth using. If you use nothing else with it, and you don't even care that it's based on physics, just as a messaging tool, what'll even be when we get the Python and the Java and the TypeScript version, if there's interest in it, if the transpiler generates Python, if you have your address record, let's say let's say your server is, I don't know, Java, for example, and the client is TypeScript, or your server is Kotlin, you create your address and you run the transpiler, you can generate that same object in the other language. And now you can mix this between languages. You can send a message from Java to Python and reconstruct the clone on the other side, language independent. So talking about the future of this, the future is to support multiple languages so that we have a generic way. We're all governed by the laws of physics. We all live in the same universe that's governed by the same laws. So then the language itself doesn't matter, because you can have a proton in Python, you can have a proton in Java, you can have a proton in Kotlin. As long as the behavior is following very closely the standard model, we can transmit data between languages without any layer in between. It'll self-replicate itself and make clones on the other side. So one big direction, like I said, we're at the tip of the iceberg right now, but building multiple language versions of this is definitely a project. For anyone who's interested in writing a transpiler, you can hit me up, because I think that would be really cool. Right now I'm trying to do a lot. I'm also building, which I'll show some other time because I know you got to go. I have a custom socket server using WebSocket communication, and that's how I'm transmitting. I'm using radiation. But one last thing for the future, because I know you have to go, but is
The folks a
really
preview of what's coming.
Yeah. One thing is, like I showed, let me go back into the RunMe. Chemistry, I'm just scratching the surface of what can be done. Here, I'm creating polymers. When you can think of rows, you have a monomer, which is one molecule. A polymer is, you can think of it as rows of molecules of the same type, which works out perfect for chemistry. So I have a polymer of address rows, and part of my test case, I can write a rudimentary SQL filter. I'm going to filter with this polymer that's passed where name is name to, where city is city to, and activate the polymer. And I expect to have one row back, which it did. It basically did select. I don't have ands and ors and all that. This is just a proof of concept, but chemistry and catalysts is a whole project in itself. To really have powerful query language in physics using chemistry and catalysts, that's a big project. So we can go down. People have good knowledge of chemistry and can apply the principles of chemistry and enhance this library, or want to work on it and push chemistry in a new direction. You're welcome to join. My knowledge is stronger in physics and chemistry, so having extra chemistry knowledge would really be helpful. Chemistry and programming. Electronics is really interesting, and I'm kind of excited about working on this one. If you looked at some of the documentation, I have the ability to create diodes and capacitors. If diodes are one-way flow of data. So if I change atom 3, it has a diode relationship to atom 2, which has a diode relationship to atom 1. So the data flows one way, but if I change atom 1, it won't flow the other way. But if I'm using conductors, I can change something and it'll flow one direction or flow another direction, either way. We can create resistors. I think I have an example of that somewhere. Let me go into the dictionary. I made a resistor. Here's a resistor. Right here, every atom, you get notified when the proton value is changing, and you get the quarks. And I'll save the Z bosons for later. For the most part, by default, you're accepting the value. Whatever somebody sets, you take. But this thing could validate and decide that, nope, this is a zip code. You can't have more than 5 digits. You gave me 12 digits. So you can now reject it. And the message goes back. When you do the set, you get a tau anti-tau pair. And what that is the current value and the previous value. And if the previous value is the same as the current value, you also get part of its properties is coming back with an error message. You get back nope and a return code. And so you can use electronics and create resistors and put things together. And some of my thought is, let me go into electronics. This is some of the stuff that's coming. Components. Amplifier. You can think of an amplifier as a collection of transistors, like passing a sequence of on switches before full output can flow. If you think about an amplifier, you have basically as one transistor, one level of flow, it adds resistance or flow. If it passes a threshold, you can get more current, more current. So it amplifies. The capacitors we already got. You have a capacitance change that's already working. I didn't. Cool. Conductors, that works. Diodes work. Filter, I'm not sure.
It sounds like it's following basically just laws of nature as we know it. But yeah, I gotta pop out. You just want to let the folks know what's coming up in the pipeline. Just you don't need to physically show them. Just kind of let them know what's going on.
All right. Well, more electronics, more chemistry, more physics. Eventually, I'm not going to do it right away, but support for multiple languages. And whatever, if people in the community want to pick up something and help and work on something, I know that somebody was interested in working on a B-tree database based on, the laws of physics and building it with virtual physics. We'll see where this goes.
It's exciting stuff. I think the future is going to probably look a little brighter just because that's here. So sorry, it's a quick one, folks. But anybody wants to check this out, Eschelon's links to his repository in the doobly-doo below. Check it out, and if you know anyone else, hey, maybe a little word of mouth. I think that's how it's going to pick up. So take care of yourselves, everyone.